Welcome back to our study on statistical mechanics. In our earlier classes, we have been studying about canonical ensemble. Before that, we studied about microcanonical ensemble. Today, we will be studying about quantum systems. The systems under special conditions, they will be showing some quantum behaviors. What is a quantum behavior? We will be studying later. First of all, we will study about what are the conditions for a system to be quantum. There are a large number of properties exhibited by the systems like Stephen Boltzmann law, that is energy emitted per second is proportional to fourth power of absolute temperature. Then inside a solid, phonons will be showing some special interesting properties. A very famous quantum property is Bose-Einstein condensation predicted by Albert Einstein. All these things are responsible for some very interesting properties which are called as quantum properties in statistical mechanics. We are going to find how and why these properties are there and what is the physics behind all these properties. For that, we will be taking microcanonical ensemble once again, and we will be taking or changing that microcanonical ensemble suitable for quantum problems. Therefore, we will come back to omega, which is the number of microstates for in the case of microcanonical ensemble, which will be a function of energy, volume and number of particles. Therefore, we have to find out what is omega in the quantum situation. Quantum situation means here in this case your energy will be discrete, and you will have to consider your levels are separated, and we will be labeling the number of particles in a particular level. We will call a particular level as the ith level, and then we will say that Ni is the number of particles occupying the ith level, and then we will represent the number of degenerated levels for that ith level as Gi, and then we will find out omega for different types of systems. Okay. Therefore, Gi is called as the degeneracy also. Sometimes we will call it as Gi as the degeneracy. And that degeneracy, we will assume that it is very or much greater than 1. And then when you are considering this microcanonical ensemble, we know that 3 factors are always a constant. That is, 3 parameters are always a constant: energy, volume and number of particles. The volume means volume of the system. Energy means total energy of the system is constant, and here we will be considering separate levels of energy. Therefore, we can say that E, that is the total energy, is sum over Ei Ni, where Ei is the value of particular energy level. We will be considering different levels of energy, and we will call this as E1, this as E2 and this as E3, etc. And the number of particles occupying each state I will represent as N1, N2, N3, etc. Then the total number of particles is a constant in the case of microcanonical ensemble. Therefore, N I can say that it is always equal to sum over Ni. Similarly, the total energy will be equal to, here E1 is the energy value of the first level. Therefore, the total energy of all the particles in the first level will be equal to N1 number of particles into E1. Similarly, for the second level it is N2 E2 plus etc. Therefore, this I can write it as sum over Ni Ei. Sum over Ni Ei. This is what I had written earlier. Therefore, sum over I Ni Ei is the total energy, and sum over I Ni is capital N. Now, we will be able to see that this omega will be different for different types of systems. Whenever we are dealing with a quantum system, we have to consider what are the types of particles we are dealing with. All the particles in this whole world can be classified into 2 depending upon their intrinsic property, that is the spin. The particles having the spin equal to 0, 1, 2, 3, etc. There will be a multiple of h cut, that is 0 h cut, 1 h cut, 2 h cut, etc. Particles having spin like that. For example, the spin of a photon is 1. The spin of a phonon is 1. Therefore, these two particles are bosons. Similarly, there are second type of particles which are fermions. Fermions will be having odd integer spin. Fermions will be having odd integer spin. That is, bosons, when you are dealing with the bosons, the spin will be 0, 1, 2, etc. When I am dealing with the fermions, the spin will be half, 3 by 2, 5 by 2, etc. The best example for a boson is a phonon or a photon. Photon means a quanta of light radiation, and the fermions, the examples are electrons, protons, neutrons, etc. And these are responsible for, these particles, because of their spin, they are responsible for the quantum properties. They are responsible for the quantum properties. And when you are trying to place these types of particles in different energy states which I had shown you earlier, then because of a particular law which is known as the Pauli's exclusion principle. Pauli's exclusion principle says that no two fermions can occupy the same state. The level or the state that I had shown you earlier, in that no two fermions will be allowed to occupy. Therefore, when you are allowing these particles to distribute in different energy states, then for example, if I have one energy state and if I have some multiplicity there, this multiplicity I call it as the degeneracy, or and it is represented by Gi. And the number of particles that I can allow to occupy, this I will label as the ith state. Ith state. And if I am distributing the particles here, there is a very important principle which is known as the Pauli's exclusion principle. Pauli's exclusion principle says that no two fermions can occupy the same state. That law is not applicable, or that principle is not applicable for bosons. Therefore, when I am allowing the bosons to occupy these three, one state is there, these two multiple states are there, I can have, if the number of particles I have is Ni, if it is equal to 2, I can allow the bosons to occupy. Here I can have one particle, here I can have another particle. Then I am taking the case of bosons. Here I can have one particle, here I can have one particle. These particles, we call it as, or we say that it is indistinguishable. And when I say indistinguishable, I will be representing by some 0 like representation. If it is a distinguishable particle, I will have to label them. Then I will call them as A and B, A or B. Some labeling will be there. And in the case, the third case is that I can have the particles can be distributed here or here. And since this represents a single state, this is the ith state, in that there are degeneracies, therefore, this represents a single state. Therefore, in the case of bosons, I can have, once again I can have, or I can have more distributions. I can have two particles in the same state because there is no Pauli's exclusion principle. Therefore, this will give rise to 6 types of distribution in the case of bosons. And the equation is Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Therefore, Ni is 2, you have degeneracy is 3, 2 plus 3 minus 1 factorial divided by 2 factorial and once again 2 factorial. Therefore, this is 5 minus 1 is 4 factorial divided by 2 factorial, 2 factorial. Therefore, this is 1 into 2 into 3 into 4 divided by 4, which will give you 6. 6 ways are there, 6 ways of distribution. These are the 6 ways of distribution. 6 ways of distribution are there. Now, in the case of fermions, your omega, we will find out. In the case of fermions, you can have one particle here and the second particle here. We can have one particle here, we can have the second particle here, we can have one particle here and the second particle here. Because of the Pauli's exclusion principle, no two particles are allowed to occupy the same state. Therefore, three additional distribution which was allowed in the case of bosons is not applicable in the case of fermions, and therefore, your omega will be given by gi factorial divided by ni factorial gi minus ni factorial. And what was our gi? 3 factorial, that is 1 into 2 into 3 divided by 2, that is 2 and 2 cancels. This is 3 minus 1 is 1, therefore 3. These are the three distributions that are allowed in the case of fermions. Therefore, these are the two formulas which are allowed, which are available for bosons and fermions in the microcanonical ensemble for a quantum system. And if these two systems are at very high temperature, they will be obeying another distribution which we call it as the Maxwell-Boltzmann distribution, where we will not be taking into account this spin will not be taken into account. Then the particles are distinguishable also, therefore, we will say we will label them as A and B, then omega will be different. Therefore, with this omega, with these three omegas, that is omega, one is for boson it is ni plus gi minus 1 factorial divided by ni factorial gi minus 1 factorial, and for fermions it was gi factorial divided by ni factorial gi minus ni factorial, and for Boltzmann particles it is gi raised to ni divided by ni factorial. These are the different omegas. Then we will be able to use these omegas, and then we can use the expression for S is equal to k log omega. And also we have two equations, n is equal to sum over ni and capital E is equal to sum over I ei ni. Using these three equations, one is the equation for omega, second is the equation for energy, third is the equation for the number of particles, and making some mathematical uses. By using some mathematics, we will be able to change all these things, and we will be able to get a distribution function for these three systems together. And that distribution function is given by ni is equal to gi divided by z raised to minus 1 e raised to beta ei, where z is called as the fugacity, which is given by e raised to beta mu, which is called as the e raised to beta mu, which we will be able to get when we are deriving this distribution function. We use a method which is known as the method of Lagrange multipliers, and then we will be able to get a particular constant which is usually represented as alpha, and by substituting that alpha properly, we will be able to replace that alpha, and then we will be able to get that as z raised to minus 1. Z is called as the fugacity, and where z is represented by e raised to beta mu, where mu is the chemical potential. Therefore, this is the distribution function for these three systems together, where A will be, or you can write this expression as ni is equal to gi divided by z raised to minus 1 e raised to beta ei plus A, I will say plus A, and A will be equal to plus 1. A will be equal to plus 1 for a fermion, A will be equal to minus 1 for a boson, and A will be equal to 0 for a Maxwell-Boltzmann distribution. Therefore, when A is equal to 0, ni will be equal to gi, and you can take that set to the numerator, z raised to minus A is 0 and e raised to minus beta ei. This is the expression for your Maxwell-Boltzmann distribution. But if it is Bose-Einstein distribution, this A will be equal to minus 1 and A will be equal to plus 1 for fermion. Now, in the case of a classical system. Classical system means whenever I say a quantum system, the quantum system is basically due to the overlapping of the wave functions. That is, for example, whenever I say a quantum system are exhibited by particles in the micro world. In that micro world, the particles will be always having a wave function, and this quantum property come into play only when, if you have a very big very big box, and if you have a wave function like this, and there are no other particles or there are no other waves, this particle, a particle is here which is replaced by a wave, this particle will not show any quantum property. The particle will be exhibiting a quantum property. It will be exhibiting a quantum property if there are a large number of particles and all those particles are represented by waves. And when these waves interact or when these waves overlap, your quantum property comes into play. Only when these particles overlap or when these wave functions, particles means wave functions overlap, the quantum particles will be coming into play. And if these wave functions has to be overlapped, then there will be a large number of particles in a particular volume, or the number density must be very, very large. Classical system means, for example, if I have an ideal gas, the particles will be well separated, and then that type of systems we call it as a classical system. There is no interaction between, there is no quantum interaction between them. That is, there is no interaction between, or there is no overlapping of the wave function. The interactive potential means it is a classical system. But when they become a wave in the micro world, and if these waves are interacting or when they are overlapping, the so called quantum properties comes into play. Therefore, if we want a quantum property, definitely the number density must be very large. And therefore, number density means the number of particles in a particular level must be very, very large. Therefore, what we have is we will not be able to get a quantum condition. The statistical mechanics does not directly provide a quantum condition. Statistical mechanics only provide a classical statistical mechanics condition. That is, you have this equation Ni is equal to Gi divided by z raised to minus 1 e raised to beta ei plus a. Our statistical mechanics says that from this equation we can have a classical statistical mechanics condition, not for a quantum condition. When will the particle exhibit classical behavior? The particle will be exhibiting classical behavior if the number of particles in a particular state is very low. If it is very, very low, that is, all the particles are not crowding into a particular state, they will be exhibiting a classical behavior. Therefore, Ni must be very, very small. If Ni is very small, Na has to be very small, then this whole thing must be very large. Or this equation Ni is equal to Gi z raised to minus 1 e raised to beta ei plus a is there, and if Ni has to be very small, then this quantity must be very large. And this quantity very large means this a is plus 1, minus 1 or 0. Therefore, we will neglect that a, or this must be very large, and this can be very large only, that is, this equation I can rewrite as e raised to beta ei divided by z. Therefore, this has to be very large, and this has to be very large means this z must be very, very small. That is, if z is much less than 1 or of the order of 10 raised to minus 5, etc., if it is very, very small, then 10 raised to minus 5 goes to the numerator, and then this will be very, very large. And at that condition, you can say that the system will be exhibiting classical behavior. Therefore, you have this expression. Therefore, I will neglect that a. Ni is equal to Gi divided by e raised to beta Ei divided by Z, or this Z raised to minus 1 plus A is neglected. Therefore, Ni will be equal to Gi Z e raised to minus beta Ei. For the system to be classical, or the system to be exhibiting classical statistical mechanics, therefore, I will take summation over both sides, then this will be equal to n, this will be equal to n. I can say, I can take that Z outside, sum over Gi e raised to minus beta Ei. This is nothing but the partition function, and we are taking a classical system, and classical system means particles will be point objects. Your point objects will be there, it will not be exhibiting any wave nature. Therefore, this is nothing but this will be the partition function for an ideal gas, which is given by V by lambda cube. We had derived that earlier, V by lambda cube. Therefore, what we have now is n by V is equal to Z by Z divided by lambda cube. I can take this lambda cube to my left hand side, n by V lambda cube is equal to Z. But the condition for a classical system is Z is much less than 1. Z is much less than 1. Therefore, for a classical system, n by V lambda cube must be much less than 1. Or traditionally, we write this as number density. I write that as small n, or n lambda cube is much less than 1 is the condition for a system to be classical. And when I say much less than 1, what I mean is of the order of, for example, 10 raised to minus 1, it is 0.1. Therefore, it is not much less than 1. 10 raised to minus 2 is equal to 0.01. That also is not much less than 1. When I say it is much less than 1, it must be greater than 10 raised to minus 2. It must be much less than 10 raised to minus 2. That is, it can be 10 raised to minus 3, 10 raised to minus 4, etc. Therefore, for a system to be classical, your n lambda cube must be always, your n lambda cube must be much less than 1. Then your system will be exhibiting classical statistical mechanics. Otherwise, the system will be exhibiting quantum behavior, or system will be exhibiting quantum statistical mechanics. This is the condition for classical statistical mechanics. Therefore, what will be the condition for quantum statistical mechanics? If the system is not obeying this condition, for example, if your n lambda cube is, n by V lambda cube is not much less than 1, it is less than 1. For example, if the n lambda cube, small n lambda cube is equal to 0.1, it will be a quantum system. If 0.01, it will be a quantum system. And if it is n lambda cube is equal to 1 or 2, etc., it is not much less than 1, it will be a quantum system. Therefore, these are the conditions, or I can say that even if it is n by V lambda cube is equal to 1 plus 1, n by V lambda cube is greater than 1, n by, there are different equations for different equations much greater than 1. All these, this equation, all these equations will be suitable for a quantum statistical mechanics problem, quantum statistical mechanics problem. But there is only one and only one condition for a classical statistical mechanics, that is n lambda cube is much less than 1. Therefore, that is the idea behind, that is, these are the equations that we derived. That is, if any system is not obeying this condition, n by V lambda cube much less than 1, it will be a quantum system. Therefore, this equal to 1, it can be nearly equal to 1, it can be much greater than 1. All these will be satisfying the conditions for a quantum system. Therefore, if I want a quantum system, there are two conditions. One is that its lambda must be, the number density must be there must be a proper value for lambda, and that lambda is actually, the lambda is the de Broglie thermal wavelength. Therefore, n by v lambda cube, if it has to be, for example, if it has to be equal to 1, for example, if a number density is some 10 raised to 25, your lambda is actually h divided by 2 pi m k t whole raised to half and whole raised to 3, that is whole raised to 3. Therefore, this h is 6.6 into 10 raised to minus 34, and this T is the absolute temperature. Therefore, when you substitute that, there is this h is 10 raised to minus 34 whole cube. Therefore, in order to account for that, your temperature must be very, very low. Only then this 10 raised to 25, if it has to be nearly equal to 1, it must be multiplied by at least, if it has to be 1, it must be multiplied by 10 raised to minus 24. Therefore, this temperature will be making it will be deciding factor for making the system to be a quantum system. With this, we will be, I have just introduced what is meant by a quantum system, and we will be next, in the next section, we will be deriving the how to make the system to be a quantum. Thank you.